Okay, I'm rolling. All right, so we're talking about different states of matter, or
So, if you Google how many states of matter there are, it'll tell you that there are 5 for some stupid reason. And everybody knows that there are 3 states of matter that you know on a basic term. The stuff you deal with down here on Earth, which is solid, liquid, gas. That's the stuff you'll mainly deal with on Earth. You're never going to run into plasma on Earth. And so I argue that...
So, wait, let's just do solid. Solid would be
So
ice,
solid
liquid,
yeah.
Water that we drink, and then
anything that kind of...
steam would be gas.
You can kind of tell what a solid is. It's like the stuff that resists pushing. And the reason that happens is it's like when you have atoms that are cold enough, they don't have enough energy, they won't have enough energy to kind of break their bonds. They're bonded together and they're stuck in this shape. Now, if you take ice, for example, which is the going solid, we use water because it's just the easiest way to demonstrate this. You take the ice and you melt it, and what you're melting it is you're giving it enough energy so that the water molecules can break out of their little lattice structure and slide around each other, but they don't have enough energy to get entirely away from each other. Heat them up enough, they get so excited that they can actually move apart from each other and they don't have to be stuck together. And that's steam, right? So 3 states of matter, and there is a 4th state of matter called plasma, which is this stuff in the sun. Now, teachers will often say that plasma is when you heat up gas really hot past its gas point, but that's not entirely true. What plasma really is it's gas that's been ionized, which means it has like a charge, like negative or positive, so it can be affected by a magnet or a charge.
Okay.
That's why the sun has, it can have those big like arcs of plasma coming off of it. It's the magnetic field affecting it. But so you don't have to necessarily have super, super hot gas, but it does help. And so Google says that there's a 5th state of matter called a Bose-Einstein condensate. And while it is a state of matter, I don't think it falls into the standard states of matter. Because if you count Bose-Einstein condensates, there are a lot of other states of matter I feel you have to count. And the reason is here's what a Bose-Einstein condensate is. When you cool matter down to a low enough temperature, like I'm talking like a few maybe kelvins, like 1 or 2 kelvins above absolute zero, right? Absolute zero, by the way, is the point at which all motion on a quantum scale stops happening. So atoms don't move around anymore because heat is just particles moving, right?
Right.
If you cool them down enough, you reach a point called a Bose-Einstein condensate. And what a Bose-Einstein condensate is, it's essentially like, hey, let's take 1,000 atoms, stick them together, and when you cool them down enough, they behave a lot like one atom.
Okay.
They start acting like one atom. And
I understood that.
It's extremely useful because if you're studying, say, quantum mechanics, you can see like quantum mechanics through like a magnifying glass. I can go, I don't need to keep track of just one atom. I can keep track of one atom that's 1,000 times the size of an atom, which makes things so much easier. And it has other properties. I don't exactly know what the other properties are. I just know its applications in quantum mechanics. Now, the thing is this is a very specific state of matter. Like, I count solid, liquid, and gas because those show up a lot in the universe. You can find solids, liquids, gases, and even plasma everywhere. In fact, I'd say plasma is probably the most common state of matter. Now, the thing is, if you start counting Bose-Einstein condensates, these very specific conditions you have to meet, well, you have to start counting other ones, like quark-gluon plasmas, which are when you heat up matter so much that they break down past their proton and neutron states into the quarks and gluons that make them up. You have to start including supersolids, which are when you cool solids down enough, they get these weird factors that happen purely because of quantum mechanics. You have to include superfluids, which are fluids that when you cool them down enough, like liquid hydrogen, if you cool hydrogen down enough, it will actually achieve a superfluid state, which means it has 0 viscosity, there's no resistance. It will flow, and if I have like a vat of, say, liquid hydrogen here, and I get like a whirlpool spinning, that whirlpool will never stop. If I cool down mercury, to enough of a temperature, it gets zero electrical resistance. You have to start counting superconductors, which can quantumly levitate. And that, like, I feel like it's kind of a blurry line, but I feel like if you start incorporating something that does not occur in the universe naturally as it is now, then you have to start incorporating other forms of matter that
Right.
can only be made in a lab.
All right. Good explanation.